All right, so we are going to look at influence line for continuous beam, and we are going to deal with the three-span continuous bridge. Now let's take a look at this line beam. We'll have 10 meters, 20 meters, and 10 meters span bridge. Now we want to obtain the influence line at point E for this three-span continuous bridge. The first thing we want to do is to apply uh, a unit couple moment at the point. If you apply unit couple moment at the point, the qualitative influence line will have it as this. And let's label the point as we have it on the board: A, support B, support C, and support D. Okay. Now our point of interest is point E. We intend to obtain the influence line at point E. Now, having applied a couple moment, we are going to have the deflected shape in this format. We'll have it in this format. Now, like I said, step one is applying hinges at point E. Step two, applying a unit couple at E. So when we do that, when we apply a hinge, we allow a rotation at the point E. So we have the couple causing a rotation at point E. So a unit moment, 1 kilonewton meter is applied. Now, of course, we know we are going to have some shear resistance, which we have arrow E prime and arrow E prime prime. Okay, so we have that. Of course, we know due to symmetry, we are going to have both of them to be the same. We are cutting the center line of the three-span bridge. Okay, so let's look at span ABE. Now, if we consider span ABE, we'll have the algebraic sum of vertical reaction as this: RA plus RB minus RE equal to 0. Now we need to obtain the moment about a point. Let's take a moment about point E. So we say summation of moment about point E to be 0. So if we work that out, we'll have 20 RA plus 10 RB to be equal to 1. So we can call this equation equation 2 rather. Now, having obtained equation 2, we are going to obtain the slope deflection equations. Let's start with the slope equation for for beam ABE. So if we work that out, we have our EI plus 0 parameter. So we have RA. Let's take a cross section from our left hand side to our right hand side. So taking arbitrary point X, we have RAX squared plus RB over 2 open bracket S minus 10 raised to the power 2 plus constant A. All right, so we have the first constant of integration, having integrated our moment expression M of X. Now we proceed to obtaining the deflection expression, where we'll integrate the slope expression. If we do that, we'll have our deflection expression as this. So we have RAX 3 over 6 plus RBX 6 open bracket X minus 10 raised to the power 3 plus AX plus K, where K is our constant of integration. Now, we need to take boundary conditions in this case. Of course, we know the boundary conditions. We know already that we're going to be having 0 deflections at point A and B. And of course, at point E, we are not expecting B. At point B, we are not expecting a 0 deflection. So we're going to have a value for deflection at point E. Now let's take the boundary condition, starting with the first point, which is point A, where S is equal to 0. So at point A, when X is equal to 0, we are going to have the deflection. Putting 0 here, putting 0 here, putting 0 here. We're going to have the deflection expression, deflection to be 0. So it means our K, which is our constant of integration here, becomes 0. Okay. Now the next we are going to check out is when X is equal to 10, which is at support B. When X is equal to 10, we will have the deflection expression also equal to 0, and that expression we can substitute 10 here. This becomes 1000. substitute 10 here, this becomes 0, substitute 10 here, 10A. So the expression becomes what we have here, 1000 RA over 6 plus 10A equal to 0. So this, we call this equation 3. So this is the expression for that. Okay. Now the next we are going to do is to obtain the value for A, which is our constant of integration. Of course, we know our second constant is 0. So our first constant, if we work at equation 3, which is this equation, if we work it out, we should have A to be 1000 RA over 60. Okay. Having gotten A, all we need to do is to check for deflection at this end, which is when x is equal to 20, and that is at the point E. So when x is 20 at point E, we should have the deflection to be 8000 RA over 6 plus 20A. All right. And so we can call that equation 4. Okay, so we already know what A is, so we can just quickly substitute the value of A obtained from equation 3. I will bring it here. When we work that out carefully, we'll have our deflection at that point, x is equal to 20, to be 1000. All right, so when we substitute the value when x is 20, we have the expression. Now substitute the value for A obtained from equation 3 here. We have A to be minus 1000 RA over 60. So if we substitute that here, we are going to have the general expression at point X is equal to 20 meter, which is at point E. That is deflection at that point becomes all we have here as 1000 RA as the deflection. So we'll call that equation 4A. Okay, so we've obtained the deflection at point E, which is 20 meter away from support A. So having gotten that deflection, we look at the other side of the beam. If we look at the other beam, which we call beam ECD, you will see that we can as well do the same for this particular beam. Okay. Now remember, we've taken the algebraic sum, we've gotten equation 1. Now let's go to beam ECD. So looking at beam ECD, we start by obtaining the algebraic sum of vertical reaction, and we have the expression as equation 1. The next we do is take moment about point D. So we did that, and we have our expression to be 20 RD plus RC equal to 1. We call that equation 2. The next we are going to carry out is a moment expression for this particular beam. So if we work that out, RDX, we take it from this right hand side to the left hand side. So we have the expression RDX plus RCX minus 10, open and close bracket. Okay, so the slope expression is this. We have constant of integration. Let's call it A again. We have the deflection expression. Having integrated this, we have this RDS raised to power 3 RC over 6 plus RC s raised to power x minus 10 raised to power 3 over 6 plus AS plus B. Okay, so this is the expression for the deflection. Now, like we did in the other beam, taking boundary conditions, of course, we know deflection at support is 0. So we have two supports. We are going to take deflection. Since we are starting from here, RD, taking that, now let's take, we'll say deflection at point E due to beam ECD, that is at point X is equal to 20. We're talking about ECD. Is equal to deflection at point E due to beam ABE, which is the previous beam which we worked on. You can check, you can revise that video. So it's equal. So if that deflection is equal, of course, they will be equal at that point. So we will have that the deflection of that point E at X is equal to 20, which is for this particular beam. For this particular beam, which is this beam, we'll have that expression to be 8000 RD over 6 plus 1000 RC over 6 plus 20A. Okay, now from this equation 3, we can obtain A to be equals to 100 over 100 RD over 6. So we're going to substitute the value for A into our expression in this case. So if we do that, we'll obtain uh, the value for this deflection at E for this particular beam ECD. We'll have that value for deflection to be 1000 RA minus 100, 1000 RC over 6 minus 1000 RD, all equal to 0. Okay, so by the time we equate these two, substitute for A, equate. All right, so we have already substituted the value for A is equal to 100 RD over 6. So if we plug it into this expression, we'll have the expression to be 1000 RD plus 100 RC over 6 as equation 4. Now, having obtained this equation 4, of course, we know that this equation 4 represents the deflection at point E, okay, with respect to beam ECD, okay? So we are going to equate that deflection with the deflection obtained from our beam ABE at point A also. So if we do that, this expression equal to our expression of 100 RA, and we'll collect like terms. Accordingly, we'll have it equal to 0. So we'll have a new equation, which we call equation 5. So as it stands, we have basically 3 equations. We have equation 5. We've reduced equation 4 to 5. Equation 5. We have equation 1, and we have equation 2. Now, looking at these three equations, you observe that we have 4 unknown in these all expressions. We have from equation 1 to equation 5. We have 4 unknown, and we have reduced the equation to 3 equations, which are equation 1, equation 2, and equation 5. All right, so I will obtain equation 4. The next we are going to do is to obtain the last equation, which will be obtained by equating the slope at point D due to beam ECD, and also the slope at point E due to beam ABE. All right, so when we equate both slope, we're going to obtain the fourth equation. All right, so we're going to look at the slope at E due to beam AB. Now the slope at E due to beam AB, the slope expression we have it this way, like this. RAX raised to power x2 over 2, RB over 2, x minus 10 raised to power 2 plus A. Now we are going to check the slope at point x is equal to 20. If we do that carefully, we are going to have the expression for the slope to be this 200 RA plus 50 RB plus constant A. Okay, so now recall that we have our A from this particular beam, which is our constant, to be minus 100 over 6 RA. So if we substitute that value of A into this expression we have when x is equal to 20, we're going to have the slope expression to be 200 RA plus 50 RB minus 100 RA over 6. All right, so this gives us the slope expression. We can call that equation 6. Now we're going to look for the slope at point E when we are taking into consideration the beam ECD. Okay, so if we do that, we're going to have the slope expression as this: RD over 2x squared plus RC over 2 open bracket x minus 10 raised to the power 2 plus a constant A in this beam. Remember, the A here is quite different. Okay, so from the A in this particular beam. Okay, so we say recall the A in this beam here, we have it to be minus 100 RD over 6. So we are going to substitute that value from this beam ECD, the value of A in beam ECD. So if we do that at point X is equal to 20 in the slope expression, we are going to have that expression to be rewritten as 200 RD plus 50 RC minus 100 over 6 RD. So we can call this equation 7. So we've gotten equation 7. Now we are going to equate equation 7 because we know that equation 7 and equation 6 are equation for the slope at point E. And of course, we are going to have equal slope because the beam is symmetrically divided at the midspan between the two uh, adjacent span. Okay, so we are going to have equal slope, and because of that, we're equating equation 7 and equation 6. And if we do that, we'll have the final expression of equating 7 and 6 to be 1100 RA over 6, 50 RB plus 50 RB minus 1150 RC, or equal to 0. All right, so we can rewrite this expression, which is this equation 9. We can rewrite the equation again to have it as equation 9. Okay, now the next we are going to do is to solve this equation. Now we can see that we have the four equation: equation 1, equation 2. We have equation 5 on the other side of the board. So the last equation, which is the equation of equilibrium for the slope, which we've just gotten as equation 9. So we have four equations, and we have 1, 2, 3, 4 unknown. So this equation can be solved because we have four unknown and we have four equations. So we'll solve for this. When we solve for this, we are going to have the values for RA, RB, RC, and RD. Now, solving for that, we discover that RA is 0.109, RB is minus 0.0699, RC is minus 0.1799, RD is plus 0.1399. So we can approximate these values while we solve for them. So, okay, so let's look for this exact slope. Remember, for us to obtain the influence line at point E, we must divide the deflection expression by the slope at point E. So first of all, let's obtain that particular slope at point E. So we say slope at point E is the slope when S is equal to 20 for beam ECD. So we can substitute that value and find out the value for the slope. So next we are going to say the slope at E due to beam ABE. So call it beam ABE. All right. So we write the slope expression in terms of X. We can say the slope when X is 20, we substitute 20 into that expression. We'll have that slope expression to be 200 RA plus 50 RA plus A. Okay. Now, but recall that we have our A, which is 100 over 6 RA. So we can substitute that into A. If we substitute that into A, we'll have the entire expression to be this, which is equation 7. Now, equation 7, we're going to equate equation 7 to equation 6. We've already gotten equation 6 like we know before. So equating equation 7, which is this equation, to equation 6, we are going to have the resultant equation, which is equation 9. So this equation 9. Now, of course, by the time we put these equations together, starting from equation 1 through equation 5 to 9. So I said equation 1, 2, 5, and 9. So we have the four equation for the four variables. All right. So we can solve for each of those variables using matrix method. We can solve this problem. We have that RA is 0.109, RB minus 0.06999, and RC minus 0.17999. ROD will have it as 0.13999. So we can approximate all these values. If we do that, we have the final values for it. Now from beam ABE, we say that we have the total slope at E to be twice because the beam is symmetrically divided, so we are expecting a similar slope for both sides. So I said 2 times the slope when X is equal to 20. If we work that out, multiply facing the variables, their values, we have the expression as this. That then be right. So we have the exact value for the slope to be 33.333 over EI, which is flexural rigidity. So we say now that deflection at S is equal to 20 for the beam ABE. We'll have that expression. Substitute the value for RD and RC. We'll have it as 110 over our flexural parameter. All right. So in the influence line at that same point, X is equal to 20 meters, which can just obtain the ordinate by dividing by the slope 33.33. If we divide the slope at that point, we be able to obtain the ordinate of the influence line. The general expression for the influence line is obtained by dividing it by the total slope at E. We have it as Y, which is a function of X. We have it on the board. All right, so this brings us to an end to this lecture of a three-span continuous bridge. You can check out other videos to obtain the area AB, BC, and CD. Thank you very much for watching. I'll, I remain your host, Engineer Obaga. I'll see you in the next class. Have a wonderful time. Stay cool.